and later on I will, so this lesson is beginning to be recorded. All right, hopefully my sound is coming through on the recording. I'll find out soon enough, and I'll at least, we'll be able to see the notes that I'm writing as we talk. Okay, so sorry about that. I'll figure out how to make this room work later. So let me get my notes out. Hopefully I have my notebook back in here. No, I left my notebook upstairs, or did I? I think I will run and grab my notes. Okay, so I'll be back in just a moment. So I'm going to go up and down the wrong way. You'll have to see that. All right, and I'll be back in about 2 minutes. You can talk about that. Just stay in your seat. There we go. You can see that pretty well. Okay. So let's begin. We were going to begin at 9:30. Wow, we're 15 minutes in. So we can 45 minutes. Let's see what we can do in the next 45 minutes. All right. So you all can see my iPad. I apologize to those at home. They're going to be able to watch it later. Looks like most of them are staying. So I left them a note. I don't know. Hopefully they can see it. I hope they're going to get a snack or something. Okay. So we've gone 3D now, right? So if I say P, let's say 2, 0, -1. What is the meaning of 2, 0, -1? What, yeah, those are x, y, z. Okay, so these are x, y, z values, right? So we're 3D now, right? Now you could. It's kind of hard to think about this, but we talked about this in the last class. If I were looking at a corner of a room, let me pick a color that shows up better. If there's a corner of a room right there in yellow, okay? Like pretend we're kind of looking at that front corner. Unfortunately, it's not a clearly defined corner. You would see kind of the floor from your perspective going that way. I'm going to draw the Y. Another direction would be kind of along the front wall. Depending where you're standing, maybe it would look kind of like that. Okay? Jenny, can you turn the other light off and the one that I turn off on? Because I realize you have the light on closest. That's probably better, right? And then we have a direction that's up like that. Okay? Now I told you that this was X, Y, and Z, and most of you made a good attempt of plotting points in 3D on the homework. Is it easy to make it look 3D on a flat paper? No, it's not easy. Okay? What you really need to be able to do is rotate it around in order to see it well. That's how we know where objects are. Okay? In fact, let's if you do this right now. Okay, I'm going to stand right here. Everybody stand up. Everybody, you can't do it if you're over there. Everybody take like one big step in that direction. Okay. Oh, actually, go back to your regular place. Go back to your place. My head is the point in 3D space. Look at my head relative to what's behind it. I'm trying to make this accuracy. Take one big step that way. What happened? What did you notice about my head? Yeah, it shifted against the background. Okay, so it's now lined up with things in the background that are more to the right. Okay, back and then one big step the other way. Sorry about people on the ends. So the way you know where my head is that you're seeing it shift against the background. Okay, back to your seat. All right. So by moving around in space, we know where things are. Okay. So let's say you wanted to throw a dodgeball at my head. You never take that shot, but let's just hypothetically do that. As you're kind of moving around, you get a good sense of where I am, and you can. And according to the dodgeball, you just need to get a straight line at the person. Okay. So you are seeing the line. You have a line of sight. So if you have a point in 3D space, it just happens in 2D space too. Well, you might see that it's along this line of sight. To know where it is, you actually have to locate it along two different lines of sight. Now, for objects that are close to us, how do we get two lines of sight very easily? We all have two lines of sight. Yes, I saw Annika, do that again. Yes, we have two eyes, right? So if you wanted to thread a needle, right, you can do it because you can hold it close enough where you have two lines of sight near your head. Okay. So many animals have eyes more to the side. They don't see in 3D. They don't see stereoscopically because their lines of sight don't overlap. Okay. So if you're into horses, horses can't sew. They can't thread a needle. All right. Because they wouldn't be able to see the overlapping line of sight. Hooves make it kind of difficult too, but even if they had hands with their, their eyes out on the side, okay, they don't get two lines of sight at an object that's up close. Right? Now, when an object's further away, those lines of sight become so parallel that to see where something is in the back of the room, I kind of have to walk around to gauge how far away it is. So those of you who play golf, if you want to know how far away the green is and you see the flag, if you kind of walk a little bit to one side or the other, you get a sense of how far away the flag is that's sticking on your ball. Okay? So we need two lines of sight to see something, which is why it's really hard to put a dot on a page and make it a 3D. Okay? We need to be able to move around to really identify in the brain where that might be. Any questions about that? Now, what does the advantage horses have over people? Why do they have their eyes out on the side of their head?
They can see all around.
They have, yeah, they can see behind them really well. Okay, if you were, a tiger and you wanted to eat me for lunch, you could sneak up behind me pretty easily. It's hard to sneak up on a horse. Okay, so anyhow, there's when your survival depends on not getting eaten, having eyes to the side. Almost see behind you is a really good thing, okay? But it's not very good if you want to, read and write and thread needles. Okay, so that's horses are just terrible at that. Let's see. Moving along. Look. There we go. So we have this point. Let me erase some of that so that we can keep the notes together here. So those are x, y, and z values, and we know we can go out x, we can go over y, we can go over z. We could rotate those coordinate systems around, though. We're going to see, like, x could be, there's actually some graph paper that you can buy for plotting in 3D, and they actually do this. They make x like that, and y like that, and z goes up like that. Okay, so that's just a rotated version of the same thing, because if you're looking at the corner and you walk around, you kind of see it from different angles. So there's actually graph paper that has these little shapes like this, and then you got another one over here that looks like this, and you can kind of go so many units in the x direction, and then so many units in the y direction, and then up those vertical lines in the z direction, and it actually looks more 3D when we use that kind of calculator. Okay, we're not going to focus on plotting points, all right? I just need for you to understand there are these points in 3D space, and we'll, it's kind of difficult to plot them on a 2D paper, but we can do our best. Okay, so we switch back to white here. Q is another point, -1, 2, 3. All right, and R, looking at the point 0, -2, 1. Okay, so we have those 3 points. I'm going to switch up on me there, sorry. We have those 3 points. And we learned back in the 2D stuff, we could make vectors. Okay. I could have a vector PQ. What would the vector PQ look like? Jeremy?
2 negative 2, 0.
Yeah, so how do I get from P to Q? Actually, that's not quite right. What would I have to do in the X direction to get from P to Q?
Oh, wait, you did 2 minus negative 1.
Yeah, so you would have to go 2 minus -1. All right? Somebody else, how do I get the Y value? Let's just go to nothing. How do I get the Y value?
0 minus 2.
0 minus 2. Jenna, how do I get the Z value? Yes, so PQ would be the vector that goes from, that is 3, -2, -4. Okay? So if you started at P and add 3 to the X, oh, I'm sorry. PQ, oh no, we have this all backwards. That would actually be not PQ. What did we just find? We found QP. Let's just do that. Let's just change this. QP. This is QP. So if you have 2 things and you want to find the change. If today I have $20 and tomorrow I have $25, what is the change? Positive $5. I'm getting richer. Okay. So I gain $5 if I go from 20 to 25. So you have to take where you ended minus where you began. Okay. So the original numbers would not have been PQ, it's QP, because the first numbers are the P value. So you're ending with the P and you're starting with the Q if you're doing that one. So we just found QP. All right? But that's a vector that would connect P to Q. Remember, we had some notations will come up in the homework when you were working with 2 points. Okay. In this case, Q is the initial point. Okay, and what was the name for P? P is the terminal point. Oh, I guess Q doesn't show up real well. Okay. Let me go not dark background and see if it looks better. That's easier to read, right? Let me move this over just a little bit. I think that's easier, except the yellow. I'll avoid yellow now. Okay, so I think it's easier on the light background for you all to see it. Okay, it flips the white and black. Yellow is still yellow. Okay, that's going to be more color to work with. Let's say that we wanted to find the point, so that's QP. All right. And I'm going to just use this as vector U right now. Let's make a vector V that is QR. I want to find QR. Okay. So my terminal point is R. So I need to get from Q to R. Okay. What do I have to do in the X direction, Annika? To get from Q to R, I have to go. Yeah, 0 minus -1, which is 1. I have to go up 1. Okay? That, Chris, what do I have to do in the Y direction to get from Q to R? Yeah, so I need to go from 2 to -2, right? So what is that? Yeah, it's going to be -4. Okay? Or if you want, it's -2 minus 2. Because we end at -2 and we started at 2. All right? Moving along, okay? For the Z coordinate, Josh, help me out.
Sorry, You don't just look at here, anything from.
Yeah, I couldn't get it to work, so we tried for about 10 minutes and.
Sure. You could keep
Play
teaching,
around with
yeah.
that while we keep going here, okay? So the z direction, what about that, Sophia? How do I get from 3 to 1? Which would be -2, okay? So vector v would be -1, or 1, -4, -2. Question?
When you say Q is what point?
Q is the initial point, okay, and P is the terminal point. All right, so then let's do a UV, let's go with W next, okay? What points have we not connected? We did Q and P, and Q and R, what haven't we connected? P and R, let's do P, R. So that means we're going from P to R, okay? Sarah, how do I get from P to R in the x direction? What was that? 0 minus 2, so I get -2. Okay? How do I get, by the way, Mr. Unum, recording this so that, hopefully there's sound in it, but if not, so hopefully they can get it later. How do I do that in the y direction, Pauline? Yep, so it would be, 0 minus -2, so we got, what was that in total? -2, right. Okay, so I'm sorry, yeah, you're going to be at -2 minus 0, which will be -2. Okay, so you go from 0 to -2. We had to go -2 in the y direction. Abby, what do I have to do in the z direction? Okay, so yeah, we went from -1 to 1, so that was a total of, right, 1 minus -1, right? So we get 2. To get from -1 to 1, you have to go up 2. Okay? So there are a couple of ways you can do it. You can do the second point minus the first point. Or you can do, you can just reasonably figure how much did I have to go to get from the first point, the initial point, to the terminal point. Okay? So anyhow, you may write them out or you could just get there. Okay? So we have 3 vectors, U, V, and W, that are connecting those 3 points. All right. Now let's do another thing. Okay. I want to know what is the size of vector U, the magnitude. And this comes down to what we had done the other day in our. Oh, by the way, can those of you at home hear me now? Not sure. So this is still being recorded. So we know how to get the magnitude of the vector in 2D. What do? We learned the 3D Pythagorean Theorem. Okay, so in general, we just take delta x squared plus delta y squared plus delta z squared you learned. Okay, so the vector is telling us how much x, y, and z are changing. So if I want the magnitude of vector u, what do I specifically put in? Go ahead, Georgie, help me out. And make sure you talk loudly because there's lots of noise. So Georgie, how would you get the size of vector u?
U would have 3 squared plus negative b squared plus.
Yep, and I'm just going to square them right out. So it's 3 squared. And remember with the -2 squared, when you go to put it, if you use your calculator, just square 2 so you don't accidentally subtract the square. Okay. So you're going to get 9 plus 4 plus 16, so 13 plus 16, 29. It's not a nice one, it's irrational, but that's how long vector u is. Okay? So once again, we just use the Pythagorean theorem. This is Pythagorean. Okay, so how long is it? It is the square root of 29, just using a Pythagorean theorem, just like we did when we found the magnitude of 2D vector. You all did it very nicely at the celebration. Okay, so I know you know how to do it in 2D. We just extended to a 3D Pythagorean theorem. All right, we can do the same thing. Amy, help me out there. The size of V. I want the magnitude of V. Square root of Yep. So it's root 21, okay, and magnitude of W.
Square root of negative 2 squared plus negative 2 squared plus 2 squared.
Okay, and that's a square root of 12. So notice I just put the squares right in. You can do that, or you can put in negative 2 squared. If you do negative 2 squared, though, make sure you do the negative up to squared, which is 4. Okay. Make sure you don't do the negative of 2 squared, which is negative 4. Okay. When you add up the legs, you have to, the hypotenuse needs to be the biggest thing. Okay. So each one of those squares needs to be positive once it's squared. So look out for that. So that's how you get the magnitudes of vectors in 3D. You understand it in 2D, and you understand that the Pythagorean theorem can be used in 3-dimensional space. That's a pretty easy change to make. Okay. Continuing on. Let's see. Any questions with magnitude in 3D? Let's add them in 3D. Okay, so let me just copy down U was, I get these down here just so that there are 3, negative 2, negative 4. V, notice I'm using the vector brackets. V, 1, negative 4, negative 2. Okay, and W is negative 2, negative 2, 2. Spread that out a little bit. So I'm just recopying them so they'll stay on the screen as we're talking about them. Okay, so there are the vectors. Let's just do simply U plus V. I want to do U plus V. It's 3, negative 2, negative 4, plus 1, negative 4, negative 2. All right, Jonathan, what do we get if we add U plus V? Oh, Jonathan, sorry. Okay. Oh, by the way, we could rewrite all of these in unit vector form. Let me do this underneath here. This is 3I minus 2J. What comes next in the alphabet? K. So K is the unit vector pointing in the Z direction. I is 1 unit long pointing in the X direction. J is 1 unit long pointing in the Y direction. K gives us a third dimension. And it's 1 unit long in the Z direction. V likewise can be written as I minus 4J minus 2K. And W could be rewritten as negative 2I minus 2J plus 2K. So if you wanted to, you could add the I's to the I's, the J's to the J's, and the K's to the K's. So that's relatively easy in either component form or unit vector form. Let's just do one that's slightly trickier. Let's do 2W minus V. Okay, so that would be 2W, negative 2, negative 2, 2, minus V, 1, negative 4, negative 2, and you can do this in component form or unit vector form. Okay? Jeremy, first we give you 2W. What is 2W going to be?
Negative 4, negative 4, 4.
Okay.
Also, what is W? Is that?
Oh, that was the vector, that was PR. So we had defined W to be PR. Oh, I guess I shouldn't write too far to the left. I'll try to write a little more centrally so that we don't go off the edge there. Okay. Just we need a wider. Anyhow. So we have these 3 vectors. Okay, so 2W is that. We're just going to subtract 1, negative 4, negative 2. Josh, take me to completion here. Exactly. Any questions on how Josh got -5, 0, 6? So it's very easy to do addition and subtraction and scalar multiplication, like 2 times a vector is very easy when they're in component form or unit vector form. Right? If we were trying to add 2 vectors where we were given magnitudes and directions in 3-dimensional space, that gets kind of crazy. But if I give a direction, you'll learn later, we will not do this in 3D. Because you would have to have a direction relative to how much you rotate. Let's say I'm sitting in this corner of the room. Okay, and I want to point to the red thing on the wall. Okay, sorry, those of you at home, you won't see this. Okay, I would be pointing in the X direction, and I have to rotate a certain amount. Let's pretend I have like this mechanical tank. Okay, so I would say rotate, a certain angle here. But right now, I'm going to be shooting the L in Wilberforce School. Okay, so then what do I have to tell it to do? Raise the barrel up. Okay, and now I can, with my little laser beam, hit the red thing on the wall. Okay, and would there be a magnitude, a distance from where I am to where the red thing is? Yeah, so I don't really need to know how far it is to aim my laser, okay? But I need 2 rotations in order to get there. So it gets very complicated because you have a azimuthal angle and a polar angle, okay? Which is exactly how we get around the globe, okay? If you look at longitude and latitude, it's based on whoever has the laser pointer being where? In the very center of the sphere, okay? There really isn't somebody with a laser pointer. But it's hypothetically, and we tell them, okay, to kind of go a certain angle east or west, okay? Those are your angle of longitude, okay? And then, that's an azimuthal angle, okay? And then you tell it to angle upward or downward from the equator, right? And that gives you a polar angle. So those things, we would do 2 angles. So we would prefer to work with component form. It's very easy to talk about X, Y, and Z or component form. So we'll avoid using magnitudes and directions because we need more than one direction. You will be old enough to handle that someday, but today is not that day. All right. Moving along. Dot products. Okay, we know that if we wanted to take, let's just say, vector A and vector dot it into vector B, and let's just say A was 1, 2, and we're going to dot that into vector B. That's really bad handwriting. Vector B, which is -3, 4. Help me out, Sophia, how do I do that dot product?
1 times -3 plus 2 times 4.
Yes. Okay. Now the key is the answer is simply a number, so it's -3 plus 8, which is 5. Okay. The answer is just a number. Okay. It is not a vector. So let's use intuition. What did Sophia do? She multiplied the X component times the X component, and the Y component times the Y component, and added their sums. So you sum the products of the components. All right? Let's go back to vector U and dot it into vector V. So U was 3, -2, -4. Whoops, I accidentally got a dot in front of that, which wasn't intended to be there. That's a smudge, not an actual negative. Okay. 3, -2, was it -4? -4 needs to be dotted into V was 1, -4, -2. So those are 3D. Now, by the way, for the 2D, what can you pretend their Z values are? 0, and if you do 0 times 0, you get 0. So we could just say, well, you could treat it like you could make them 3D, okay? A and B could be re-expressed with one more dimension, and they just happen to be, if we're thinking of the floor and the ceiling direction being the z direction, they just happen to be along the floor, okay, parallel to the plane of the floor. U and B, though, are pointing in kind of all directions, all right? So if I want to get U dot V, Abby, what do you think you do? Yep, so you get all of that. So 3 times 1, okay, so 3 minus, or plus 8. Plus 8 again, so that looks like 19. Key is, the answer, is it a vector or a number?
Number.
Right, so the key is the dot product is a value, would be a better way of saying that, not a vector. That will be important because later in the week, we're going to start learning about vector cross products, and it's about a perpendicular product, and the answer is a vector. Okay. So when we do dot products, the answer is just a number. Any questions on how we do the dot product? Okay, so I could do more of those, but oh, well, let's do this one. Let's do U dot I. Ooh. How do we do that? What do you think? Let's see. So U is 3, -2, -4. If I wanted to do the unit vector I, how can I represent the vector of one unit in the x direction? Amy, what would you do? So I want to express I as a vector. It's the unit vector in the x direction. So I'm going to do U dot I, but I'm trying to figure out in the second bracket how to put I. How do you think you could express a unit vector in the x direction? Yeah, so what do you think the x value is? What was that? 3. Not 3. It's a unit vector, so the x value, I see a lot of people, Jordy, you're saying it's 1. How much is it pointing in the y direction? So how much would the unit vector I point in the y direction? Is it pointing in the y direction? So I points in the x direction, right? So is it pointing in the y direction at all? No, so how do I say it's not pointing in the y direction? It would be 0, right? And is it pointing in the z direction? Nope, so I would put 0 there. Oh, this is a super easy dot product. And what am I going to get for this dot product? 3 times 1 plus 0 plus 0. Okay, which is just 3. And by the way, what was 3 the same as? The x component of u. So this is the x component of u. All right? So if I want to find the x component of u, I could take the vector u and dot it into I. How could I find the y component of u? U dot j, and if I want the z component of u to pop out, I do u dot k. All right? So in general, we can talk about our unit vectors. I is 1, 0, 0. J is 0, 1, 0. And K is 0, 0, 1. Okay. Oh, this brings us into a whole new thing we can do. We'll talk about this more tomorrow. What's going to be true about I dot I? Didn't hear you. Oh, somebody's in the waiting room. Okay, Enoch is in the waiting room. All right. Thank you. I should have seen that. Okay. So, what do you think is true about I dot I? You took 1, 0, 0, got it into 1, 0, 0, what do you get? You get 1 times 1, right, which is 1. So if you get I dot I, you get 1. What about I dot j? That will be 0, because you get 1 times 0, plus a 0 times 1, plus 0 times 0, and so that is 0. What's true about I and j? Are they parallel? No, they are perpendicular to each other, so their dot product ends up being 0. What about jk? Then j dot k would be 0. What about k dot k? 1, okay? So when you take a dot product between unit vectors, the unit vector times itself is 1. The unit vector times one of the other unit vectors will always be 0. We're going to see some crazy things happen when we do cross products, where I cross j gives you k. Well, okay. We'll talk about that later, okay, not today. Right? So we do cross products, I, j gives k, okay, whereas I dot j is 0. Okay. So they're completely different kinds of multiplication that'll be useful in each case. You get adding vectors, you get dot products, okay, angles between vectors, right? Angles between vectors. Okay, so angles between vectors. It turns out U is still true. This thing that I just wrote is still true. What was that thing called? The dot product theorem. Okay. So there's one angle in there. That angle is the angle between the vector u and the vector v. So we can use the dot product theorem to still determine the angle between two vectors. Right? So I have u dot v equals uv cosine theta. So let's do u and v. Okay. So in fact, we have u dot v already figured out. We look back in the notes, u dot v is 19. Whoops. U dot v was 19 for our example. The size of u, we did that a while back, was the square root of 29, and the size of v was the square root of 21. And the magnitude of v was the square root of 21. Right? So it doesn't matter that they're three-dimensional. We have a dot product, right? And remember, so you kind of missed this a little bit, I saw in your formula sheets. Cosine of theta is the parallel factor. Okay. So if they're completely parallel, cosine of theta should come out to be 1. If they're anti-parallel, cosine of theta will come out to be -1, and if they're perpendicular, cosine of theta will come out to be 0. Right? So we can solve for the cosine of theta, just like before, it's u dot v over the magnitude of u times the magnitude of v. So in this case, the cosine of theta is 19 over the square root of 29 times the square root of 21. All right. So you're going to have to take the inverse cosine of that number, 19 square root of 29 square root of 21. At this point, it's brute force. But before we put it in our calculator, do we need to worry about quadrants when we're working with inverse cosine?
No.
No, because where does the inverse cosine work? Everywhere from 0 up to 180. Will vectors ever be more than 180 degrees apart? No. So we love using inverse cosine for this because we don't have to worry about, that the quadrant issue. All right? When you get an answer, just shout it out. 39 point, I'll just say 6 degrees. Okay? So those are 39.6 degrees apart from one another. Any questions on that? So if you know how to do the dot product in 3D, and you know how to find the magnitude of the vectors in 3D, then it's no harder than what you did before in order to find the angle between the vectors, okay? Now, this is not the angle relative to the x-axis, the y-axis, or the z-axis. This is the angle between two vectors, okay? Now, I'm going to introduce what I just said a second ago. Alpha is equal to the angle relative to the x-axis. Beta is the angle relative to the y-axis. Does anybody know the next Greek letter? Alpha, beta. By the way, alpha, beta, those are lowercase alphas and betas. That's where alphabet comes from. The next letter is gamma. Okay. So this is the angle relative to the z-axis. Okay. Now let's pretend the x-axis is towards the back of the room. So if I have a vector, like pointing over here, it actually makes a cone around the x-axis. Okay? So if I tell you what its angle is relative to the x-axis, you can, in space, visualize a cone, okay, that would wrap around the x-axis. Likewise, that same vector, here's the y-axis. It could make another cone. That's at angle beta, where the central angle of the cone would be beta, as it wraps around the y-axis, okay? Now, if you have those two angles, if you have those two cones together, they will intersect right on where the vector is, okay? Now, that vector also wraps around the z-axis. So if you put its tail at the origin, okay, it would make a cone around the z-axis as well, okay? Now, there's only one direction in space that has the x, y, and z angle all being the same, right? So if you had all three angles, you would be able, if you do a angle relative to the x-axis, y-axis, and z-axis, you could start here and say, oh, let's go out a certain angle from x, and then a certain angle from the y-axis, and a certain, you can put those things together and figure out what direction to point. Okay. So sometimes we want to be able to get angles relative to one of the axes. All right. So let's take vector u, which was 3, -2, 4. Let's find alpha for u equals -3 to, get that right again, -2, -4. Okay, so it's 3 in the x direction, -2 in the y direction kind of points it that way, and -4 it's kind of pointing down over there somewhere. We put those things together. All right? So, how do we find the angle relative to the x-axis? What do we know is parallel to the x-axis? What vector has a length of 1 and is parallel to the x-axis? I. Okay, so what we're going to do, let's use I is parallel to the x-axis. So when I want to find alpha, I can find the angle between u and I. What do you think I do if I want to find beta? Question. Oh, Enoch is trying to come in again. There we go. What do I do if I have to find u? I'm sorry, u relative to the y-axis. I'll find the angle between u and j. And if I want to find the angle relative to the z-axis, I'll find the angle between u and k. Okay? So what I can do is I can use u dot I should equal the magnitude of u times the magnitude of I times the cosine of alpha. So it's nothing new. There's nothing new here. Okay, but this does simplify. U dot I, we looked at that already. If I take U dot I, that was 3, -2, -4, dotted into 1, 0, 0. So U dot I just gives me 3, which was the same as the x component of U. So U dot I is the x component of U. Okay? What's true about the magnitude of I? It's 1. Okay? It's a unit vector. By definition, unit vectors have a size of 1. So we can get rid of the I in the dot product theorem. Okay? And so that, what does that leave us with? It leaves us with the following. We can simply say the cosine of alpha is U of x over U. It's the x component of U over the size of U. Okay? What do you think is true about the cosine of beta? Using all the same logic? Instead of U of x over U, over magnitude of U, it would be U of y over the magnitude of U. And cosine of gamma is just going to be U of z over U. All right? Then you're going to use an inverse cosine to find those angles. We are essentially out of time. Okay, so those angles, we don't use them too often, but when you do want to find the angle between a vector and one of the axes, you can do a dot product between the angle and the corresponding unit vector. Okay? You'll see those for a few homework problems, but that's it. We actually made it through everything I wanted to do in the hour and 45 minutes. So well done. I'll stop this recording. Mr. Yoon said that you all should have your lunches in room 300. So you're not staying here because another class has to come in here for next period. All right, so on Mondays, let me